So, color Doppler. Our discussion began today. We talked a little about sector size, the region of interest of our color, Doppler box, and how that can change our frame rate based on sector size, depth, and all of that. Talked a little bit about the color velocity scale, laminar versus turbulent flow when it aliases, setting our, maybe I didn't mention that, but setting this scale. Color gain. Well, we did mention the scale because you can go low, high versus low and adaptive and all of that stuff. So we mentioned the Doppler shift, and that you guys are taking this with norma, so we understand that we have to be at an ideal angle with the blood to get the greatest Doppler shift, to see the greatest Doppler shift. We talked about the Doppler equation and how that is rearranged to solve for velocity. And we don't have to rearrange the equation, but we have to know how to utilize the equation to get what we want. And on test purposes, like I said, for your registry exams, you're going to have to know when variables change, what happens to the equation, right? The angle representing the difference between the ultrasound wave direction and the blood flow direction is an angle theta. And that's just a word. And interesting, when the theta equals 0, cosine is 0. So we talked about that. If blood is moving at 0, 180 degrees, the ultrasound wave assumes a perfect alignment with the blood cells. So theta would be 1. The only part of the Doppler equation we don't know is velocity, and the machine extracts this velocity information for us through a process called demodulation and autocorrelation with blood. So the velocity difference between the source of our wave and the blood is the Doppler shift. And we talked about theta. This is theta, and theta is just a symbol. Could be X, could be A. And what's interesting to know, theta is, I think I looked up, theta is the 8th letter of the Greek alphabet and was considered the symbol of death at one time during the Greco-Roman days. So it's and we talked about the demodulator and how it extracts the Doppler shift. How you can rearrange the equation algebraically. The machine does this for us, thankfully, to solve for velocity. And here we have our Doppler frequency equals, and then we have velocity in here where we've rearranged the equation so that our velocity equals this right here. Cosine remains the same variant at the end there. This tells you about how the formula breaks down here and what everything means, and the formula breaks down what everything means. Again, it's done within the architecture of the machine, the computer system. We talked about cosine values that are important for us to know. Basically 1 and 180 opposite of each other, polar opposites, 30 degrees, 150 would be polar opposites of each other. The percentage here, this is 100%, right? This would be 87% of our true velocity, and that's okay to make an error to that point. Anything beyond that, though, is going to be counterintuitive for us. If we only have a 70%, if we have a 70% error in measurement, that's really not helpful for us in detecting the true Doppler shift. And at 90 degrees, there is no Doppler shift. So we basically said 0, 30, and 90. And if you're doing vascular ultrasound, 60 degrees is where you land at. That's about the best you can get in vascular ultrasound. That's exactly a 50% drop-off. And the machine knows that, so it adjusts for that setting. We looked at the screen, tore it down pretty well, so I'm not going to spend too much time on that, but basically the information that's on the screen, including our Doppler scale, our grayscale, our low velocity scale, red and blue, BART, and all that stuff, our 2D data, our color Doppler data, and all of that. And again, BART, blue away, red towards, blue away, red towards. We talk about towards, we're talking about towards our transducer, away from our transducer. So it's either painted red, it's painted blue. Slower velocities are in here, higher velocities are this way, slower velocities are in here, higher velocities this way. This is our Nyquist limit, which is based upon our pulse repetition frequency. This is 73 centimeters per second. And just remember that if our Doppler shift exceeds 73 centimeters per second, then we can't measure it. It's just going to wrap around, and it's going to become like a yellow color that we can't really discern. The machine can't discern which way the direction blood is going. We have a sector size when we do our blood measurements. We played with the sector size and region of interest today, primarily on our apical views of the mitral valve, and the setting that defines the region of color Doppler interrogation within the sector is called the color box. And the effect that has is setting color blocks as narrow and shallow as possible, allows for a maximum frame rate and velocity scale, yielding the best temporal and flow velocity resolution. Temporal means time, right? And this was a demonstration we put up on the board. Where this one here is, this is hard to see here, but this color box is covering our LVOT, showing blood coming out the LVOT, and we're getting a really nice smooth flow there. There's virtually no change in velocity of the blood right there. It's all blue on the way out. You can see it lights up a little bit as it goes through the aortic valve. That's typical. Where it's going to increase in velocity, it goes through that orifice. And here you can see our sector box is just too wide, and we have trouble picking up that flow that's coming through the aortic valve. Our sector box is way out here, and that's going to decrease our frame rate to about 15 frames per second, whereas this one here is as high as 35 frames per second according to this. That's pretty hard to hit, but here the frame rate is, I can't see that, maybe it's like 50, 60 hertz over here, and here you see the frame rate drops down to 19, 20 hertz. And we talked about that. That's because of when we put our color box on, which occupies the space right here on the mitral valve, you see this is without any color, and over here we got color compare on. Put our color box on, the transducer has to create a box not just this big, but this big. So that's going to, it's doing two things at the same time. Therefore, it's going to decrease the frame rate the machine, the rate at which the machine can display that image, and that's going to drop down substantially. So we want to keep that, like I said, 18 or above. In this case here, it's 19 hertz, and that's fine. And we do that. We keep the frame rate above a certain range, so that the heart doesn't end up being when the frames are put together, like in the movie we're making, when the machine is scanning through this heart, it doesn't make it look jumpy or anything. It's smooth. We talked about our color gain button. We demonstrated that after the class. This allows us to demonstrate optimal color flow for the structures we're evaluating. We talked about increasing our gain till we see that overgained scattering that goes on, and we bring it back down just below that, so we should be at the proper gain when we do that till the speckling disappears. So it amplifies the color signal to demonstrate color flow in the structures we are evaluating. And we talked about this right here, where it's an optimal setting for color gain, where this is too high a setting, high scale, low scale, high gain, low gain, and the optimal gain, and so on and so forth. We really concentrate on optimal and too much gain or too low gain. We want to make sure we're evaluating the regurgitation appropriately. We're telling the doctors a certain amount there, and we know it's either mild, moderate, or severe. Well, if we use this high gain setting, that's not going to, they can't even differentiate what's in there. They use a low gain setting, and it doesn't look like there's anything there. So we got to make sure we're able to optimize our settings as sonographers, to have the knowledge base to know how to optimize our settings so we're actually showing the true amount of blood that's traversing the mitral valve into the left atrium during systole. Our color velocity scale, instrument setting used to optimize color flow based on the range of mean velocities, usually represented as a number, and so on and so forth. Heart default is around 50 centimeters per second, and we showed the color velocity scale. That's this right over here. So that's our scale rate. You can see our scale over here in the right hand corner. We talked about the blood velocity scale over there in class. And here's our scale over here, and we see our centimeter scale over here. Looks like it's around, I can't see that, 56 maybe. So with this, you can see here that our blood regurgitant jets coming down from the LV into the LA, actually up. We're just upside down in echo. And this blood here is hard for the machine to determine which direction it's going, but we know it's kind of going in this direction, and we can see our scale here that it's going away from us, and therefore it's going to be lighter blue, and it's going to alias because it's going too fast for the machine to determine which direction it's going in. Therefore, it's going to turn that cyan, sort of a yellow color, if you will. I didn't mention this, and we'll mention this in Echo 2, and that is, you got to remember that this blood was pumped back into the left atrium. See, we get the pulmonary vein filling here, the right upper pulmonary vein. And also remember that this blood that's going back into the left atrium, there's also blood in the left atrium, right? A little bit in there during systole. And this is going to entrain with that blood in there. So the eyeball method, although heavily relied upon, you got to remember, if this hits the blood in here in the left atrium, this blood's coming through, regurgitating back, hits blood that's already in there, it's going to mix in with that. So it can be a little bit confusing, if you will, if this is the true jet or not. But that's why we do our quantification methods. We have a low setting that we talked about on the Doppler optimization settings. We have a low, high, medium, and adapt. And these low settings are good for interrogating the pulmonary veins with signals of very low, and also interrogating the hepatic veins in the liver where the IVC dumps in there. This is a low setting. We demonstrated that. We're looking at the intraatrial septum here, and we can see that in the normal setting or the high flow setting, we don't see anything here. It's almost no blood at all in the atria, which moves very slowly. Put it on the low setting, however, and we reveal blood is actually in that area, right? So this blood in this area is just moving much slower, and on an improper setting, we can't see it. We correct our setting, and we can see the blood, and we can see the direction flow of that blood. We talked about how the machine generates the color map. It's a pulse wave technique, and it uses multiple scan lines with these little pulse wave markers in it. And you got to think about that. That's bing, 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 going back and forth here, and going back and forth, back and forth, back. Each one of these is represented in multiple scan lines through this area. And so you can see how that would take a lot of time and a lot of demodulation, if you will, to figure out which direction this blood is going. You can see how we would be very much dependent upon speed and pulse repetition frequency, if you will, and why there would be a potential for aliasing based upon this multiple sample volume technology that's happening in here. And it's going to create this grid-like structure, if you will, if you were to try to picture this, how it's happening. And then we showed this grid-like structure that's all these multiple sample volumes and what have you, and this doesn't show nearly as many that are in there. This is just a representation, illustrative. You can see the pulmonary, right upper pulmonary vein, blood coming in red towards the transducer, and you can also see blood up here that's sort of in that yellowish range where the machine doesn't know to assign it red or blue because it's picking up speed there for some reason. We don't know that based on this picture, but that's what happens. And we can see what turbulence flow represents here, red to yellow here, and we have this turbulent flow here, and we have a blue to cyan here, where the blueness is representing turbulent color here. And that's basically what the machine does. This would be a variance color map that we really don't use. We did demonstrate we have a bunch of color maps to use, and we typically use color map 1 or 4, something like that. The variance map isn't used too much in most places I've worked, although probably in the lab setting, something like that, it would be. We showed this one here, centimeters per second. This is our pulse repetition frequency. This is the variance map here, and we show red towards, turbulent flow turning a little yellow, red away, turbulent flow turning a little cyan, like green, like it is over here. We talked about how using the baseline adjustment, remember the color is flowing this way in mitral regurgitation. This is our left ventricle up here. It's regurgitating back into the left atrium. And we're going to try to determine, using the continuity principle, the quantity of blood that's going back into there. And utilizing the continuity principle, we can adjust our baseline. The baseline always moves when you're trying to look for a Pisa, trying to determine Pisa shells in the flow convergence zone right here it's called. You always move the baseline in direction of blood flow. So flood's moving this way, our baseline is going to move with the blood this way. And we typically move our baseline down until we can see a really good solid Pisa shell in here. And we can right here. We can see this is pretty well defined. We can actually see this flow. It looks like the same color as this flow down here. So this is a good Pisa shell. And I showed you that we moved our baseline down to about 31 centimeters per second to get this. So that's our aliasing velocity. And changing the baseline creates aliasing. So the blood would alias typically 60 centimeters per second either side if we move this back up to the middle. Positive 60, negative 60. But we're going to move it down here, so it's going to alias much sooner. And at aliasing, we're going to use that effect to actually help us take a measurement here of a Pisa shell, the flow convergence zone. And that's going to be put into the formula to help us calculate an effective regurgit orifice area. And therefore, from that, we can actually determine regurgitant volume and regurgitant percent of blood going back into the left atrium. We talked about low flow color situations. We just mentioned that. This is a PFO, an ASD. Depends how big it is really to interrogate the intraatrial septum here. We use low color flow setting to better see an intraatrial septal defect if we have one. And we typically will see that on a much less scale with regular Doppler color settings, our settings at 60 centimeters per second. But this just brings it out, putting on this low flow setting, and lets the doctor see basically just how much is crossing over. It's a little more accurate with that low flow setting. We talked about the laminar versus turbulent flow and regurgitation. We talked about how that exceeds the scale and how the scale, back to the scale, how the scale determines if it's turbulent or not based upon velocity and how it paints it turbulent, this cyan green color, because it exceeds the Nyquist limit and it doesn't know which can assign it blue, it can assign it red, so it ends up in this category over here where yellow and white end up being the cyan type color. We looked at our screen on our machine and we can see that our pulse repetition frequency is 4,923 Hertz. That's the number of lines it can draw into and out of the color blocks per second. It can sample information in the color box, in other words, 4,923 times per second. That's our pulse repetition frequency. Our color gain at 70%, we can change that gain. Our wall filters, we see where they are in that same side of the screen there. We can adjust our wall filters just like we can in pulse wave Doppler, continuous wave Doppler, and our transmit frequency shows up there. Our pulse repetition frequency, I'm not sure if I mentioned this in class, and I apologize, is limited by the max depth of our color box. If we get that depth correct, we get the best pulse repetition frequency we can find rather. And that's the end. I'll post this for you.